Today we'll cover part 3 of integration by substitution, which is section 5.3. And please remind me to reopen the homework, okay? I'm going to reopen the homework so you guys can work on class if you have not finished it. And after I'm done with this video, after you're done watching the video. So last class we left on problem 10. We finished it according to Karina, so we're going to move on to problem 11. So here, I'm going to select what's inside the radicand, x minus 1, to be u. And from here, what I'm going to do is manipulate the variables a little bit. And so I'm going to call it, I'm going to take the negative 1 to the right side, so it will be u plus 1. And on the right side, we will have x. Now, why did I do that? Well, because actually I didn't have to. Well, I don't have to yet, but you'll see. We'll need that in a minute. So right here, let's go ahead and take du over dx. Like if we're still talking about this one here, it will just be 1, right? Or we could also use du is going to equal 1 times dx. So we could just say that du is going to equal dx. Now, why did I do that? Move the 1 or add 1? Well, I did that so that I can square them both. And then I will have u plus 1 squared and then x squared here. Now, if I do that and I expand this side, I'm going to get u squared plus 2u plus 1. And that will equal to x squared. Okay, now what I'm going to do is I'm going to start substituting. So instead of x squared, the x squared that we have here, what we're going to substitute that with, it will be with this whole expression, this trinomial. So that will be the integral of u squared plus 2u plus 1. Again, this x squared is being substituted with this expression. Then, what I'm going to do after that is I'm going to have that trinomial times now this part right here, which is the square root of x minus 1. And so that part is going to be substituted with the square root of u. Remember, that's what we started with, x minus 1. So that will be times the square root of u. And then finally, for the part that says dx, that will be substituted with du. Now, what we're going to do is we need to recognize how the square root of u, if we change that, get rid of the radical, we will have u to the power 1/2. And what I'm going to do now is I'm going to distribute the u to the power 1/2 to every term here inside the trinomial. And so what that will happen is we will be adding the exponents. So that will turn into the integral of u 2 plus 1/2. That will be like the same as 4 halves plus 1/2, so that will be 5 halves. The next one will be plus 2 u to the power 1 plus 1/2, so that will be 3 halves. And the next one will be u to the 1/2 times 1, so u to the 1/2. And it's all of that in parentheses and then du. So what we could do here is use the power rule to find the integral. So that means we add 1 to the exponent, and then that same exponent will become the denominator. So for this first one, we will have u. If we add 2 halves, which is 1, 2 over 2 is equal to 1. So that's why I'm going to be saying we're going to be adding 2 halves. So 5 halves plus 2 halves will be 7 halves. And then this one is going to be divided by 7 halves. you might see it written this way, divided by 7/2. The next one is going to be 2u. We have 3/2 plus 2/2, so that will be 5/2, divided by 5/2. The next one will be u, and we have 1/2 plus 2/2, so that will be 3/2, divided by 3/2, and we also need plus c. Now let's simplify this a little bit. So for the very first fraction, we have something that is divided by 1 on the numerator, and then we have divided by 7/2. So if we multiply the outer quantities, we're going to get 2 times u to the power 7/2, and then the one on the inside will be 1 times 7, so this will be 2 7ths. The next fraction that we have is, we have a 2, so I'm going to do the scratch word here on the side. We have a 2u to the 5/2 over 1, and we're dividing that by 5/2. So if we use the steps for sandwich rule, we will have 4, remember 2 times 2, so 4u to the power 5/2, and then 1 times 5, so that will be over 5. So this is 4/5 of u to the power 5/2. And then the very last one, I don't know if you're getting the idea, but when you divide by a fraction, it's the same as multiplying by the reciprocal. So the reciprocal of 3/2 is 2/3. So 2/3 u to the power 3/2, and then plus c. Now we're almost done here, except that we have to do the back substitution to what we set u to equal to, and it's right here. So it is x minus 1. So the final answer will be 2/7 times x minus 1 to the power 7/2 plus 4/5 x minus 1 to the power 5/2. And then finally 2/3 times x minus 1 to the power 3/2. And let's not forget about the plus c. So the very last step, u gets replaced with x minus 1. Okay, so I'm sure you guys, I don't know, maybe you were able to follow, maybe you got lost somewhere. So I'm going to do a very quick recap of how we did this problem. So we started by selecting what's inside the radicand to be equal to u. And then from here, the reason that we did all that solving for x is so that we could get an x squared here, because that's what we had on this side. And so we achieved that by taking this -1 to the left side, so we had u plus 1 is equal to x. And then what we did was to square both sides. So that's how we got the row here, and then we expanded this one, and we got u squared plus 2u plus 1. And why did we do all that? Just so that we could replace this x squared here with everything that was in this trinomial. And then we took, after selecting u, which was here at the beginning, we took the derivative of u, and it was just 1, and we needed dx, 1 times dx, or just dx. So that's where we got it from. The rest of it, we had to change this one to an exponential quantity, so we have u to the power 1/2. And from here, we distributed that to every term inside the parentheses. And that's why we have this exponent. So the first one was 2, which is the same as 4/2 plus this 1/2. Because when you multiply variables, you add the exponent. So this was 5/2. And that's how we got that. After that, I found the integral by adding 1 to the exponent. So 5/2 plus 1 is 7/2. And we're dividing by that same exponent. And this was just after simplifying it. So this is the end of problem 11. If you don't understand it, I suggest you watch the video again. Okay, moving on to problem 12. Now, problem 12, it's a little different from others that we've done. So first, I'm going to rewrite it. So just to make it clear, this exponent is affecting the whole cosine x, not just the angle, which is x. So it's the whole thing to the third power. Then from there, I can break it into two factors, and I will say cosine of x squared times cosine x just to the first power, right? Because together they will give me that third power. And of course, this is dx. Now, for notation purposes, I'm just going to rewrite it. So I'm going to say cosine square x, and then times, of course, cosine x dx. So this part right here is coming from here. So once we're there, what I'm going to do, instead of selecting something to be u, I'm going to select this quantity here to be du, all of it. So if I do that, if I say that is du cosine x dx, let's think about what u should be. And so to think about that, don't think about what's the derivative of u, but think what is the integral of du, because if you get that, you will be getting u, and that's what we need. So the integral of cosine x is sine x. Okay, and so that is one of the things we're going to use, but we're also going to use a very famous trigonometric identity, and we have it here, the Pythagorean identity. Sine square x plus cosine square x is equal to 1. So because that is true, we're going to substitute this cosine square x. I'm going to solve for cosine square x right here, so that will equal 1. This is a plus, positive, sine square of x, so if I take it to the left side, it will be negative sine square x. So we do that by manipulating the Pythagorean identity, and so that cosine square x that we see here is going to get replaced with all of this. So now let's do that substitution. So we're going to have the integral of 1 minus sine square x. That's replacing this. And then for this part, remember, well, we're not doing the u substitution yet, so let's still call it cosine x dx. Okay, now since we are referring to u as sine x, if I look at this expression in terms of u, it will be 1 minus, and be careful here, so sine x is equal to u. So since I have sine square x, I should have u squared, like that. So here, this integral, instead of 1 minus sine x, sine square x is going to be 1 minus u squared. Here's the 1, and here's the sine square x. We're calling it u squared. Now for the part with the cosine x dx, that one coming from here, cosine x dx, we're just substituting that with du. Now this one is one of the easy ones to recognize. No, I'm sorry, I thought it was one of the inverse trigonometric ones, but it's not. We could actually solve it by getting the integral of 1, so that will just be u to the first power over 1, or just u, minus u to the third power over 3, and then of course plus c. Now we have that, and then we need to do the back substitution. So again, we decided to call u sine x. So now I'm going to do that. So to my answer here, I'm going to replace every u with sine x. So we have sine x minus, and this one is sine cubed x over 3, and then plus c. And of course we could say that, or we could say sine x minus 1/3 of sine cubed x plus c. That's a constant, not a 0, plus c. Okay, and that is the answer to that problem. Now, if you guys notice, we have problem 14 here, but I want to solve problem 13 first. I just needed more space for problem 13. So before we start solving this problem, I'm going to rewrite it a little bit. So we start by the integral of dx over 1. That will be this part. And then this part right here is going to be a squared plus x squared over 1. Yes, I think that's very good. Actually, we don't really need to put this over 1 here. And then, of course, we have this other part that comes here, dx, because we're integrating with respect to x. And so what I'm going to do is multiply on this numerator. So I have dx over 1. I'm going to multiply it by 1. So if I multiply by 1, I don't change anything, right? But instead of multiplying by 1, I'm going to multiply by an expression that it will be equal to 1. And for convenience, I'm going to call it a over a. And you'll see why we're calling that a over a. Then, on the bottom, what I'm going to do is I'm going to factor out a common term. And of course, they don't have any common terms, but we can make that happen. So if I say I'm going to factor out an a squared, if I take this one here, a squared, and I factor out an a squared, of course, it will be 1. So that goes here. Now, if I take this one here, x squared, and then I factor by a squared, factoring is like dividing. So, of course, there's nothing to factor because there's no a squared in x squared. But, so what we do is just leave it like that, x over a, and then square it. Okay. Now, what I'm going to do, oh, and of course, we are missing our dx. Okay. Now, what we're going to have next is going to be, we're going to multiply here. So that will be the integral of a dx over, because remember, when we multiply fractions, we multiply straight across. So a dx, and then divided by a. Now what I'm going to do is keep this 2 together, so this a will be here. So multiply. Now all of that divided by a squared times 1 plus x over a, and then square. And then, of course, dx. Now what we're doing here now is we're going to take this a and this a squared, and this a will cancel the a square. So we're only going to have a at the bottom. So now we just have dx over a. Remember, this a was canceled. And then on the bottom, this a, instead of a squared, we're going to have a. And then we still have 1 plus x over a squared. And it's all of that, of course, dx. Now, I'm going to go ahead and do my u substitution. And so that will be, I'm going to take this fraction, x over a, and that's going to be my u substitution. So u is equal to x over a. Now remember that the a is a constant, so it could be like a fraction, 1 over a multiplied by x. So of course, if we get the derivative, du over dx, that will just be 1 over a, the constant, times x to the power 0, which is just 1. So that's why we don't write x to the power 0. And now from here, for notation purposes, so what we're going to need is actually going to need du. So du is going to equal 1 over a. If we take this dx, which is dividing, to the right side, it will be multiplying. So dx will be there. And of course, if we multiply these two fractions on the right side, it will just be du is equal to dx over a. So we could just leave it like that. Yes. Okay, so now let's go ahead and do our substitution. So we'll have the integral of what we're going to do first is take this a right here. And so that a is going to be a constant that will be factored out, so 1 over a. And I say 1 over a because the a is part of the denominator of this fraction here. And so it will be 1 over a. And then on the top, instead of dx over dx over a, we're going to substitute that with du. So du here. And then on the bottom, we have this x over a, but remember we decided to call that 1. Okay, and I just noticed that actually there was a typo right here. There's an extra dx. It shouldn't be here because we already have it here, okay? So we're going to get rid of this one here and here. And so right here, just to continue, this dxa is actually being substituted by du. Remember, we got that from here. And the divided by a, we took that fraction out. It's right here. Now, right here, we're just going to substitute that with u squared. So this will be 1 plus u squared. And then, of course, we're going to have here 1 over a, and then the integral of 1 over 1 plus u squared, and then du. There we go. Now, that one is one of the formulas that you should have studied. Now, that formula is the one that comes for the integral of something that looks like this, not without the divided by 1 over a, multiplied by 1 over a. So this part right here is actually going to be equal to 1 over a, and then tangent inverse of u plus c. And so what we got to do is go back and, of course, substitute u, or back substitute. So that will be the tangent inverse of whatever we call u, which was x over a, and then plus c. And I know you might be inclined to want to cancel this a with the a inside the angle, but remember, they're not like terms. This is a coefficient, and this is an angle. So you cannot do that. So don't do it. Now, in summary, I want you to copy this somewhere where you have space. it will be very useful if you memorize them. And so there are 3 of those integrals. And so if you can recognize them, it will be a lot easier because it will save you a lot of steps. So if you have something like du, and then you have a constant or a term that is being squared, and then you have another one that is also being squared, so that you could do a substitution that looks like that. We're missing, well, no, we have du on the numerator side. So that one will be 1 over a, whatever this constant or expression is, times the tangent inverse of u over a plus c. Now, if we have, so that's one of them. Next one will be if you have du on the top, and then on the bottom you have a square root, and you have a squared minus u squared. That will be the integral of sine inverse of u over a plus c. So you can apply these rules and generalize them. Well, this is the generalization of the integrals that look like that, and you can apply them to the problems that are on your homework. Now, the new date for section 5.3 is going to be Thursday, before class. So don't try to do your homework in class or after class. Okay, and so this one, it will be 1 over a secant inverse of the absolute value of u over a plus c. So some integrals, you know, they're very complicated to solve, but sometimes they do have shortcuts, like the 3 that I just showed you. So let's do we're almost done, so let's go back to the other slides. So now we're going to apply those formulas to solve problem 14. And so the reason we're using them is because 14 looks almost like those formulas on 13. Before we do that, we're going to rewrite it. So this integral here is going to be the integral of 1 over the square root of 2 minus x squared dx. So I just wrote the dx over here on this side. Okay. Now we start with our substitutions. So if we follow the same guidelines that I gave you on this other slide, if you think about it, that problem in 14, it kind of looks like this one here. Like that one right there. And so inside your square root, you have a 2, and then you have an x squared. So the 2 is going to become a squared. So then if you want to solve for a, of course, you know that you have to take the square root. So you take the square root on both sides. So a will equal 2. And u will equal x. So let's go back to the problem. So again, we're going to take this number, 2, and that is going to equal a squared. So then the square root of 2 equals a. Similarly, we take this x squared, and that will equal u squared. Now, of course, if we want to find what u is, we will take the square root of x squared, and that will give us x. And that is nice because if we want to find du over dx, that would just be 1. On our problem, however, we're going to need dx. So if we need dx, we need to take this dx from the bottom, move it to the left side in this case. And so that would be 1 times dx is equal to du. Or we could just say dx equals du. Okay, now I'm going to do my substitutions. So instead of 2, we're going to use A. Which will be the square root of 2. So this will be the integral of 1 over, we have the square root here, we have 2 square root, and then of course we're squaring it because we want to have 2, right? This number in red. Then instead of x squared, we're going to put minus u squared. And then of course we have du here. So now that we have something that looks like that, the square root of 2, again, is equal to a, and then u is equal to x. So we can compare to our formula, and that will be the one that says something like sine inverse of u over a. So let's actually write that here, sine inverse of u over a, and then plus c. So now we go back to what we substituted u and a to be, and so that will be sine inverse of x. Instead of u, we write x, and instead of a, we're going to substitute that with the square root of 2, and then plus c. And that's it. That's the answer for it. Okay, for the last part of the video, well, almost the last problem that we have here, we are going to use the calculator, so make sure you do have one, and make sure you know how to enter this problem on the calculator. So I'm going to be demonstrating. What I would do first is get the integral symbol, so you can find that one by going to menu, then calculus options, and then of course 3 for integral. Then here we're going to get one without the limits, so without the boundaries. So we'll have, what I would do honestly is enter the fraction tool just to make sure that I enter the whole integral correctly. So in this case we will need 5 x to the second power on the numerator, then denominator will be parentheses, oops, so I need to go down here, 1 plus x, close parentheses, and then to the exponent of 1 over 3, 1/3, so that will be a cubic root, and we're integrating with respect to x, and there we have it. And so I'll just press enter, and this is the theoretical integral. That means the algebraic expression. Although it is correct, it is missing something. And that something is actually the plus c. So you cannot trust your calculator fully. Plus c. Just be careful with that. And I think we have one more slide after. This one here. Oh, this is example 1. I don't know why I copied the same slide, so that shouldn't be there. So no, we are done with the whole section. So please use this time that you have left in class to work on the exam that you weren't able to answer, the one that was given in 2015. If you are all done with it, then I want you to start working on the exam from 2016, which Stephanie will be passing around. So thank you, and please pay attention and don't act like babies, like you don't know what to do and you're completely lost, because you're better than that.